Well, next we're going to state and prove a theorem about equivalence relations, and specifically partitions. Equivalence relation partitions is the theorem. Well, let A be a non-empty set, and let X and Y be elements of the set A. And let script A be a partition of A. If this condition holds, I'm going to come to that in a minute. If this condition holds, then this is an equivalence relation on A with script A equaling this set. Well, the condition simply says that X relates to Y if and only if there is a set B in the partition with X and Y being in that same set B. And let's make sure this terminology, we're getting accustomed to it. Let's just say that A is that set with 6 elements in it. Well, there are only a finite number of different partitions you could do, so let me make one up. The partition could be, remember what the partition is, it's a collection of sets whose union equals this, and the sets are pairwise disjoint. So I could pick ABC as one set in the partition, and maybe I'll pick D all by itself, and then EF. This is just one example of a non-empty set, and this is a partition of the set. So what this is saying is if you get that two elements relate to each other, if and only if there's a set in this partition that contains them both. For example, we can say A relates to B because we found a set, calling it B. This set contains them both. And even with D relates to D because there's a set that contains both of those elements. Well, they happen to be just one element. And likewise, E relates to F, and we've almost done all the possibilities. A relates to C, B relates to C. But C does not relate to D, and D does not relate to F, for example. And then let's take a look at this last statement here. We're saying it's an equivalence relation with this collection of sets of this partition equaling this. Well, this is the set of all elements that relate to X. But we're saying for every X in A. So in my example, it looks like we should have 6 sets. We're saying that A is equal to script A is equal to that set. All of these sets, all 6 of them. This is described just like this. And that's true, it's exactly the way it is. But note, what is this? This is the set A and all things that relate to it. So, A, B, and C. This set right here is A, B, and C. This set, the same thing. It's B and everything that relates to it. These first 3 sets are exactly the same set. So, when you write out a set, you don't write out repeating elements. So I could have left either one of these and scratched out A. They're all the same set. And then D, we have to keep that one. And then E and F, I just need one of those. This time I'll scratch out E. So it turns out that it just is this 1, 2, 3 sets, which represent the 1, 2, 3 partitions. Okay, well let's prove this theorem. It's a pretty short proof. Okay, let that be a set. If all of this is true, then this is an equivalence relation on A. That's what we need to prove. So we need to prove that this is reflexive, symmetric, and transitive. So let's do the reflexive part first. Reflexive just says that X relates to X. So we first need to say that let X be an element of A, or you could use any letter for the variable that you want to. Let X be an element of A. Well, by definition of partition, X is in the union of, I'll call it B, the sets that are in script A, that partition. So X is an element of B for some set B in there. If it's in the union of them, it means it's in one of them at least. So X is in B. I'm going to reuse the letter B for some B in that partition. Well, if X is in B, then X relates to X because X is in B. This is not two different elements. So we've shown that it's reflexive. Now symmetric. Symmetric means that if X and Y are in A, in script, in capital A, actually I should say if X relates to Y, then Y relates to X. So we will take suppose X and Y are in A. Well, not all elements in A are related to each other. So I'm going to say, suppose X and Y are in A with X related to Y. We're going to have to show that Y relates to X. Okay. This means that there is some set in script A that contains both of those elements. This means there exists a B in script A, that partition, such that X and Y are both in that set B. And this is really getting technical, but I'll say hence, if X, Y are in B, then I can order it the other way. Y, X is in B, and that means that Y relates to X. And the last thing we have to prove is transitive. So if X relates to Y and Y relates to Z, we have to show that X relates to Z. So in this case, we're going to say, we're going to let X, Y, Z be elements of A with X relating to Y and Y relating to Z. All right. By definition of the partition, there exist two sets, we'll call them B and C, in that script A, such that, let's see, here, X and Y are in B, and Y and Z are in C. That's just the definition of the partition and two elements being related to each other. Well, note that Y is in both of them. Y is in this, Y is in that. So Y is an element of their intersection, which means that that intersection is not the empty set, because Y is in both of the sets, B and C, so the intersection contains at least Y. If that is the case, by definition of partition, B is equal to C. Y is not in two distinct partitions. By the definition of partition, every element of the set capital A is in one set in the partition, and there's no overlap among the sets in the partition. They are pairwise disjoint. So these two sets are not disjoint, therefore they are the same set. Okay, well, in particular, X and Z are in B. I could have said C there if I wanted to. B and C are the same set, so X, Y, and Z are all in the same set. We can call it B, or we can call it C. Okay, they're in the same set, therefore X is related to Z. And that ends the proof.